In this lecture video, we'll learn about the nearest neighbor algorithm for finding a solution to a traveling salesman problem. Welcome to the solar system, Corellia. If you haven't heard of it before, that's because my children, niece, and nephew made it up for us. Imagine that an unmanned mission is headed to the solar system, Corellia, to explore. We're looking for signs of life from the past or present. The mission must visit the 6 planets: Cephupster, Unicornia, Rivetail, Lothial, Pincktonia, and Hoth. The graph shows the time in years to travel between any 2 of these planets. The underlying complete graph here is K6, with 6 planets. Our mission must begin and end at Pincktonia, and an optimal tour that has minimal cost will be a tour that uses the least amount of time. For this example, we're going to use what's called the nearest neighbor algorithm. Knowing that we need to start at Pincktonia, we'll look at the options for traveling from Pincktonia to the other 5 planets, and we'll choose the one of lowest cost, or the least amount of time. Our options are 1.1 years to Hoth, 0.8 years to Cephupster, 4.3 years to Unicornia, 4.4 years to Rivetail, or 2.4 years to Lothial. Clearly, the nearest neighbor is Cephupster, so that's where we will go first. Now that we've arrived at Cephupster, we need to look at the next nearest neighbor, not returning back to Pincktonia. Our options are 0.6 years to Hoth, 2.7 years to Lothial, 3.8 years to Rivetail, or 3.5 years to Unicornia. Clearly, the nearest neighbor is Hoth, so we'll travel to Hoth next. Now that we're at Hoth, we need to look for the next nearest neighbor. Looking at our 4 options, the least amount of time is 1.1 years to Pincktonia. But we don't want to travel back to Pincktonia because we've already been there, so that's not an option. We can only choose from Unicornia, Rivetail, or Lothial, and the nearest neighbor of those 3 is Lothial. Now from Lothial, we'll look at our options. Again, the least amount of years is to go back to Pincktonia, but we don't want to return back to Pincktonia until the very end. The next nearest is Cephupster, but since we've already been there as well, we need to choose between Unicornia and Rivetail, and Rivetail is closer. Notice that from Rivetail, we only have one option. We need to go to Unicornia and then back to Pincktonia. Now we have a solution to this traveling salesman problem, which is a Hamilton circuit beginning and ending at Pincktonia and traveling to each of the other planets exactly 1 time. Let's calculate the total weight of this circuit. In this situation, our weight is years. From Pincktonia to Cephupster, we have 0.8 years. From Cephupster to Hoth is 0.6 years. From Hoth to Lothial is 2.3 years. From Lothial to Rivetail is 6.1 years. From Rivetail to Unicornia is 0.5 years. And from Unicornia back to Pincktonia is 4.3 years. This gives us a total of 14.3 years. Now, while the nearest neighbor algorithm does give us a solution, it does not guarantee that it's an optimal route. In fact, in this case, the optimal route would look like this, giving us a total of 13.7 years. But since this is K6, there are 120 Hamilton circuits to check. Even if we cut that in half and ignored the reverse routes, we would still have to check 60 different options. The nearest neighbor algorithm saved us a lot of time in calculating. It just didn't give us the optimal route. Let's quickly calculate our relative error. Relative error is equal to the total that we got, 14.3, minus the optimal route, 13.7, divided by the optimal route, 13.7. We find that our relative error in this case, about 4.4%. The route that we found using the nearest neighbor algorithm is 4.4% more time than the optimal route. Now let's look at another example. In this example, we will use the repetitive nearest neighbor algorithm. That's the idea of using the nearest neighbor algorithm, but starting at each site, one at a time. In this example, we have a political candidate that's touring 10 cities, and their campaign manager needs to decide in which order they should visit the 10 cities. They do want to use their campaign funds wisely. The distance between the cities is shown in the chart, and they want to begin and end at City A. They need to find the optimal route to minimize traveling distance so that they minimize traveling costs. Unlike our previous examples, these values are given to us in a table rather than in a graph. Organizing data in a table is very helpful when there's a large number of sites. Let's begin by using the nearest neighbor algorithm beginning at vertex A. If we look at all of the options for traveling from A to another city, we find that city C is the nearest neighbor. I also want to cross out the column for C so that I don't accidentally revisit it. Now that we're at C, we'll look at our options for a nearest neighbor. City A is of course the closest, but we don't want to go back to A until the very end. The next closest is city E. We'll select city E and also cross off that column so that we don't revisit it. Now we look at our options from city E. Not including A, the nearest neighbor is city D. So we'll select D and cross off that column. Now from D, our nearest neighbor is B. From B, the nearest neighbor is J, not including city A. From J, the nearest neighbor is G. And from G, the nearest neighbor is K. From K, the nearest neighbor is F. And from F, we only have one option before returning to A. We must go to H, and then from H back to A. Now we've used the nearest neighbor algorithm from vertex A. This route has a total distance of 2,543 miles. Now that we've done this process for vertex A, we need to repeat the process beginning at every single vertex. I will do a few here and leave the rest for you to finish. I'll start this process over with vertex B. Looking at the row associated with city B, we see that the nearest neighbor is C. Looking down row C, we see the nearest neighbor is A. Looking down row A, the nearest neighbor is E. Looking down row E, we find the nearest neighbor is D. Next, we look down row D and find a nearest neighbor, J. From J, the nearest neighbor is G. And from G, the nearest neighbor is K. From K, we find the next nearest neighbor is F. And finally from F, we head to H, and from H back to B. Using the nearest neighbor algorithm, now we have a route beginning and ending at vertex B. And this route has a total distance of 2,935 miles. Now let's try using the nearest neighbor algorithm beginning with E. Looking down row E, we find the nearest neighbor is C. From C, the nearest neighbor is A. From A, the nearest neighbor is C, but C has already been used. So we go on to the next nearest neighbor, D. From D, the nearest neighbor is B. Notice when we look down row B that the nearest neighbor is C, but it's already been used. D has already been used. The next nearest is A, but it's already been used. And E is where we begin and end, so we don't want to use that one either. That takes us to our next nearest neighbor, J. From J, the nearest neighbor is G. And from G, the nearest neighbor is K. From K, the nearest neighbor is F. And from F, the nearest neighbor is H. Finally, we return from H back to E. This gives us a third route. And this route has total distance 2,542 miles, our best so far. To complete the repetitive nearest neighbor algorithm, we would have to follow this process beginning with each vertex. But looking at the three that we just did, clearly the one we found beginning and ending at E is the shortest. The last thing we need to do is rewrite it as a route that begins and ends at A, since that's what was requested. Beginning at A, we'll go to D, B, J, G, K, F, H, and E. And once we reach E, we'll go back to the beginning of the list, head to C, and back to A. Now we've transformed the route with start and end at E into an equivalent route that begins and ends at A with the same distance of 2,542 miles. And that will conclude this lecture video on the nearest neighbor algorithm, along with the repetitive nearest neighbor algorithm.